Welcome to Operating Systems Unit 8 on Process Synchronization. So today we're going to talk about the critical section problem and the Peterson solution. And then please read about synchronization hardware, and I've summarized it here on the slides. So in process synchronization, that means that processes that work together and cooperating processes, they must be synchronized because the results could end up to have data inconsistencies and they won't be working with the most current results. So it's very important that you have some kind of measure to deal with the way that processes that are executing concurrently work. So this is a producer-consumer, and this just is an illustration of a race condition. And a race condition happens when the order in which instructions are executed can affect the outcome. So here we have a variable called counter, which the producer produces and then increments the counter, and the consumer consumes and decrements the counter. And that keeps track of how many items have been put into a bounded buffer for the producer-consumer problem. So here is what happens is as the producer produces and makes a copy of the counter, the consumer consumes and makes a copy of the counter, and you can have inconsistencies, and this will lead to a problem because you will be trying to consume the wrong location, or you might think it's full, or you might think it's empty because the inconsistent value that the counter holds, and that's a race condition. So there are some ways to deal with this, and one thing we want to discuss is that you could have the critical section, which is an area in the code of cooperating processes where you manipulate the critical data. And just to give you a visual, if you have an airplane and you want to book a seat on an airplane, if you allow 10 processes to be in there booking the same section of seats, you may have all 10 of those processes booking the same seat. So each one of those 10 processes would have an area in its code where it requests permission into the critical section and goes in there, manipulates the critical data. So I would go in there, I would pick my seat, and the other 9 have to wait while I'm picking my seat. And then after I pick my seat, I will free it up and allow the other processes to get in there and pick their seat. So I go into my entry section, which is an area in my code. I see if anyone else is in there picking their seat. If not, I go in there and I lock it and block everybody else out. Then I go in there, I pick my seat. While I'm picking my seat, I am using the critical data, and when I'm done, I release it. So this is the setup, and all 10 processes will have this little area in their code. And a good solution to the critical section problem should solve 3 things. It should allow only one process to be active in the critical section at a given time. It should have progress, which means that only those processes that care about getting into the critical section should partake in the decision of who goes in there. And it should not cause deadlock. So this is what's called the Peterson solution, and it works very well for 2 processes. So my suggestion to you is I put a document up that explains the Peterson solution step by step. First, it starts with 2 processes just sharing a single variable called turn, which has 2 values, 0 and 1. And then it explains how that does not work because that requires a flip-flop. Then it explains that if you have flags, so you can use 2 flags in order to allow 2 processes to share, to access the critical data. But the flag will end up causing either a deadlock or causing or not preventing mutual exclusion. So if you combine a flag, 2 flags, which is a flag for each process, with a variable, a Boolean variable called turn, what you can end up with is a good solution, simple for the critical section problem with only a few variables. Now this will not work for more than 2 processes, but what this does is it illustrates very clearly the 3, the mutual exclusion, the progress, and the bounded waiting. So, and another thing to remember is that we're going to have 3 instructions here in our entry section. And the 3 instructions in our entry section are not guaranteed to go all 3 in order for one process. What that means is P1 is going to have 3 instructions in its entry section, and P2 is going to have 3 instructions in its entry section. So P1 could set its flag to true. This flag to true indicates, yes, I am P1 and I would like to go into the critical section. Then P2 could set its flag to true. Well, I'm P2 and I would like to go into the critical section. So at this point, we have both flag 1 and flag 2 are both set to true. Then P1 will say, well, you know, I would like to go in there, but I will let P2 have its turn. So remember, this variable turn can only have 2 values, either 0 or 1. So right now, this is set to 1, meaning it's P2's turn to go into the critical section. And so if the turn was set to P2 and P2's flag was set, then P1 would have to wait, because this while condition says while P2's flag is set and the turn is set to P2, if you notice the semicolon at the end here, it means I have to wait. I have to wait until either P2 clears its flag or P2 gives the turn over to me. So this will solve the critical section problem, but you must keep in mind that these 3 instructions are not atomic. Atomic would mean if all 3 of these instructions went as one unit. What could happen is P1 could set his flag, P2 sets his flag. Turn gets set to P1, turn gets set to P2. So this way, that the variable turn is going to decide which of the 2 processes is going to get into the critical section. And then if P1 happens to be the one to get into the critical section, P1 would then clear its flag, which then in turn would allow P2 to get into the critical section. So again, I repeat, please take a look at the notes, take a look at the explanation of the Peterson solution that leads up to this. And this is a good solution to the critical section problem. It does satisfy all 3 of these conditions for a good solution, but it does only work for 2 processes. So if in the Peterson solution you were able to execute all 3 of those instructions in the entry code as if it was one instruction, that's how hardware can assist with the solution to the critical section problem. The hardware can allow you to implement locks which have all the instructions in the lock, like test and set or swap, as a set of instructions as one non-interruptible instruction, and that's called an atomic instruction. So if you take a quick look here, the critical section problem using locks is the same setup, only instead of being just implemented as software, you have hardware assist with this, where a process will acquire a lock, go in and use the critical section, and then release the lock. In the next section, we are going to talk about some more software solutions to the critical section problem. So please review the notes, and if you have any questions, do not hesitate to email me and ask, and do the exercises and read the sections in the book. Thank you.